So today we're going to be talking about Newton's laws. So last time we learned about position, speed, velocity, acceleration. So speed is a changing distance over a changing time. So if I say your car is traveling 60 miles per hour, that's a speed. And then if I give that speed a direction, then it becomes a velocity, which is a vector. So if I tell you your car is moving 60 miles per hour north, now that's a velocity. A change in velocity with respect to time is an acceleration, and that's also a vector. And then combining velocity, acceleration, position, and time gives you a set of 3 equations, and we use those to solve some word problems. So these equations let you determine the final velocity or the final position of some object at some time t in the future. The distance or position, velocity, acceleration are how things are moving. Mass is how we will describe what the thing is that is doing the motion. So mass is how much matter an object contains, and mass is a scalar quantity. So you would say some object is 20 kilograms. You don't say it's 20 kilograms to the right or to the left or up or down. And so matter, so don't trust atoms, they make up everything. So mass is basically a measure of the amount of atoms something contains. And the unit for mass is going to be kilograms. And the variable that we use is lowercase m. So when we talk about the mass of planets and stars, this is what we'll be talking about, how much stuff is in those objects. In physics, what we do is we start to combine these different things together, these different variables. So momentum is the result of multiplying the mass of an object times its velocity. And so something that you can learn from this is that you're allowed to multiply scalars and vectors together, and the result of that multiplication is also going to be a vector. So momentum is a vector. We represent that vector with the lowercase p, and the units are just the units for mass, which is kilograms, times the unit for velocity, which is meters per second. And we'll come back to why momentum is important throughout the semester and also a little bit later in this lecture. So now that we kind of understand all of these different variables, we'll talk about how Newton put all of that together to come up with his laws of motion and how that changed our view of the universe. The biggest insight that he had was that whatever laws of motion that we come up with for how things move on the Earth also has to apply to how things move out in space. So when we'll come back to his theory of gravity next class, but basically the gravity that keeps you on the Earth is the same gravity that keeps planets orbiting the sun. And then in addition to his work in this kind of gravity and motion, he also did stuff with telescopes and arguably invented calculus. There's debate about a different mathematician called Leibniz who also developed calculus at about the same time, but they did it in different ways, so you can kind of credit both of them as inventing calculus. So he did a lot of interesting science and math. Okay, so his first law of motion, if you could summarize it in one word, that word would be inertia. And in many words, what that definition of inertia is either an object moves at constant velocity unless a net force acts on it to change its speed or direction. That's a little bit more of a physics-y definition. And then a more using just ordinary words definition would be an object at rest will stay at rest, or an object in motion will stay in motion unless acted on by an outside force. Okay, so the first law invoked this idea of a force. So now Newton has to define what a force is. So a force is something acting on an object that results in a change in momentum for that object. And the variable for force is capital F, and the units for force are newtons. So he's so influential, he gets a whole unit named after him. And the capital letter N is what we use to represent newtons. But newtons are just made out of kilograms, meters, and seconds squared. So now we have a inertia, and then we need to define a force. And then Newton's third law states that for every force, there has to be an equal and opposite reaction force. Or you might hear it said that every action has an equal and opposite reaction. And so this device is called a Newton's cradle, and it, in motion, is an example of Newton's third law, and you could also argue it's a representation of conservation of momentum, which is something we'll talk about a bit later. So the ball swings down and hits the other ball, and then it stops, and so its momentum or its force is transferred to the ball on the opposite side of the cradle. And so the action of this ball hitting the other balls causes an equal and opposite reaction, making this ball swing out on the other side. So if you've studied physics at all, you have probably seen this equation, F equals ma, being the definition of Newton's second law, or the definition of a force. But it's not exactly accurate. So the definition of force is actually a change in momentum over change in time. And so when you apply that change to a momentum, not only are you changing the velocity, but you also have to take into consideration any changes to the mass. And so when you apply that to both of these variables, you get two different terms that can come out. Mass times change in velocity over change in time, and then velocity times change in mass over change in time. So the first term just becomes F equals ma that you are probably familiar with, but there's this extra term where we multiply a velocity times a changing mass over changing time. So can anyone think of a scenario where your mass or the amount of stuff that you're made out of changes over time? Maybe talk with the people next to you for a minute and see if you can come up with anything. And I'll give you a hint, it does have to do with space and astronomy stuff. So. The most common example where something's mass is going to be changing is in rockets. Just the general principle that describes how rockets work is they ignite the fuel, but that ignition is really just so that the fuel pushes itself out of the backside of the rocket. So you're changing the mass of the rocket by forcing it to expel out the backside, and that gives you a force that lifts the rocket up and fights against gravity. So if you just had F equals ma as the definition for Newton's second law, then rockets wouldn't work at all. So we wouldn't be able to get to space, we wouldn't be able to launch satellites that give us GPS and have space telescopes that let us study the distant universe without the second term in Newton's second law. So it's very important. The gravitational, so we talked about gravity last time. So this gravitational acceleration is actually the force of the Earth pulling down on you. So the acceleration due to gravity was the negative 9.8 meters per second squared. And so you have some mass, gravity is always acting on you, and so you always have some force of the Earth pulling down on you. There's this caveat of this equation only applying near the surface of a planet, and so we'll talk either next time or in a couple lectures about how we modified this equation for when we're dealing with things like orbiting the sun, a planet orbiting the sun. So which of the following is true about the force that the Earth exerts on you? Yeah, so this is a conceptual question. A lot of people think that the Earth exerts a bigger force on you just because the Earth is bigger than you. But according to Newton's third law, every force has an equal and opposite reaction force. So the force of the Earth pulling down on you has to have an equal and opposite force, and that's the force of you pulling on the Earth. So the correct answer is the last one. Okay. Weight is something that sometimes gets confused with mass, but they are two different things. So weight is a force, and we already saw that mass is how much material is inside of an object. So weight and mass are not equal to each other. Another name for weight is the normal force. And so this is the force that, so if you're standing on the ground, this is the force that the ground exerts on you. So if we think about forces for a second, Newton's first law says something will stay in rest or stay in motion unless it's acted on by a force. Then we said gravity is a force that's acting on you, the Earth is pulling on you. So If there was only the force of gravity pulling on me, then I would be falling towards the center of the earth. So there has to be some force that's stopping me from falling through the ground, and that is called the normal force. So that's the force of the ground, or if we think about this ruler on top of the table, it's the force of the table acting on the ruler. So there has to be something that's stopping you from falling through the ground towards the center of the earth, and that's called the normal force. When you step on a scale to measure your weight, what you're actually measuring is that normal force. So the number that the scale reads out to you is the normal force, or your weight. So the big takeaway here is weight and mass are two different things. So how is mass different from weight? So mass is the amount of matter in an object. You can measure that in grams or kilograms. But weight is a force, and that would have units of newtons or pounds. We'll do some examples of how your weight will change in an elevator. But first, let's answer this conceptual question. So on the moon, the acceleration due to gravity is smaller than it is on the Earth. So which of the following of these is true? Good. So the force of gravity is what gives things a weight. So if you change the gravitational force or acceleration, then you're going to change the weight. So less gravitational acceleration means less weight. By me, let's say I got into a rocket ship and I went to the moon, I haven't changed how much material is inside of my body, so I haven't changed my mass. My weight just changes because I have a different gravitational acceleration that's pulling down on me. So mass doesn't change when you go to different planets or the moon, but your weight can change. Okay, so if you encounter any problems where they're talking about you traveling in an elevator and they want you to calculate the weight of the person, these are the steps that you do. First, you figure out if the elevator is traveling up or down. Then you determine what direction the acceleration of the elevator is. So if the elevator is speeding up, then its acceleration is in the same direction as its velocity. Or if it's slowing down, then its acceleration is in the opposite direction of the velocity. And then you use Newton's second law, which for most things is just F equals ma, to solve for the weight of the person. So I think we have an example where we can put this into practice. Okay, so the problem says an elevator starts from rest and moves upwards at an acceleration of 2 meters per second. If a 100 kilogram person was standing on a scale, what would the scale read? Okay, so I have my person in an elevator standing on a scale. They tell me that they're going to start to move upwards, so their velocity is in this direction. And if they start from rest and they move upwards, then that means their acceleration is also upwards. velocity points up and acceleration also points up. There's a 100-kilogram person standing on the scale, and we want to know what the weight of that person is. So the way Newton's second law works is I just need to add up all of my forces acting on, so this little sideways looking m is actually a summation sign, or you can write net, and that just means to add up all of your forces. So this person has a gravitational force pulling down on them because they're in the vicinity of the Earth, and then they're standing on a scale or the bottom of the elevator, so they have some normal force that's pointing upwards. Or we can call it the weight, since we're talking about weight in this problem. Okay. So the weight is pointing upwards, so we'll give that a positive sign. Gravity is pointing down, so we'll give that a negative sign. And then mass times acceleration, the acceleration is also up, so we'll give that a positive sign. Okay, weight is what we're solving for. That's what the scale would read. So let's isolate the weight. So we add the force of gravity to the other side. Oops. The force of gravity we saw earlier is just mg. The mass of the person is 100 kilograms. The acceleration that they're moving with, we were told, was 2 meters per second squared. Mass is still 100. And then the gravitational acceleration, we'll say it's approximately 10, just to make our math easier. And so the person's weight would be 200 plus 1,000, so 1,200 newtons. And if you were to compare that to the person standing on the scale in the elevator, but the elevator's not moving, their weight would be the 1,000 kilograms. So by standing on a scale in an elevator that's moving upwards, the scale reads a bigger number. If the person had been traveling upwards, but they were slowing down because they made it to the floor they were trying to get to, then their acceleration would be pointing down, and this would be negative 200 plus 1,000, and so their weight would read 800 newtons. So depending on the configuration of the elevator, the scale will either read a bigger number or a smaller number or the same number as if you were just standing on something that wasn't moving. But why are we even talking about elevators at all? So an interesting thing happens what if the elevator starts accelerating at the same acceleration as gravity? So in other words, what if I cut the cable on the elevator and the elevator just starts free falling? Okay, so now my acceleration, so we cut our elevator cable, and now my acceleration is downwards, and it's the same acceleration as gravity. So now if we try to calculate the weight again, now we have mg minus ma, so the a now is negative because it's pointing downwards, but g is equal to a, so we'll get 100 times 10 minus 100 times 10. And now your weight is 0. So this is called free fall, or weightlessness. So if you are trying to measure your weight in an elevator that's free falling, the scale will just read a value of 0. What this has to do with space is, if we think about what an orbit is actually perpetual free fall. So the reason why astronauts in the International Space Station are floating around in space is not because there's no gravity there. It's because they're falling at the same rate as the space station that they're inside of. So what orbit really is if I took this diving board and I started jumping off of it, and I started jumping, trying to go further and further away from the diving board, if I could jump far enough or fast enough in this direction, eventually I would miss the Earth. So if I jump off straight down, I'm going to fall towards the Earth. If I jump a little farther out, I'll still hit the Earth. But if I jump really far out, now I'm trying to fall downwards towards the Earth, but I'm basically missing every time. So here, I'm trying to go towards down, but down actually brings me over here. Now the force of gravity is pulling me this way, but I have some velocity that's already in this direction. So I'm kind of falling in this direction and I end up here, and so on. So orbit is basically a special type of free fall. And so that's why the astronauts in the International Space Station are floating. It's not because there's no gravity up there, it's because they have the same acceleration as the space station that they're inside of. Okay, so mass is how much stuff something has inside of it. The weight is a force that you could read on a scale. And objects are weightless when they're in free fall, but their mass does not change. And so we have Newton to thank for our understanding of all of these things. He came up with the laws of motion and gravity. He realized that whatever laws cause motion on the Earth have to be the same laws that cause the motion of the planets. And then these are the laws that he came up with. An object inertia, an object at rest stays at rest, or an object at motion stays in motion unless acted on by a force. Then he defined what a force was. For this class, we'll just use mass times acceleration, but just remember that there's another component that deals with the changing mass, and that's how rockets work. And then the third law, for every force, there's an equal and opposite reaction.